So good morning and welcome to this second lesson on polymers. This lesson is given in the frame of the class Materials and Their Properties of the Federal University of ABC. So during this class, we will introduce the thermal transitions of amorphous and semi-crystalline polymers. We will present common polymer processing techniques. We will introduce some important additives, and finally, we will think about polymer recycling. So during the first lesson, we introduced this polymer classification. We distinguished thermoplastics and thermosets. So thermoplastics are polymers that can be softened and melted several times and reshaped. In this case, if we apply temperature and eventually pressure to the polymer, it softens and melts, and so it can flow. So we can give the shape to this molten polymer, and if we decrease the temperature, the shape will be fixed. The material will become more solid, and the shape will be fixed. If we want to give another shape or reprocess thermoplastics, we just have to apply again temperature and pressure. And so, since this process can be performed many times, we say that thermoplastics can be recycled. So, in this class of thermoplastics, we find linear and branched molecular structures. So, it is we can find polyethylene, polypropylene, polystyrene, polyamide, polyethylene terephthalate in this class of thermoplastics. On the other end, we have thermosets that are polymers that can only be shaped during initial fabrication. So let's remember, in thermosets, we have cross-linking between the chains, the polymeric chains. If the density of cross-linking is low, we have an elastomer, we have an elastic material. So it is a case of rubbers. On the contrary, if the cross-linking density is high, we have a much more rigid material. And so this high cross-linking density are present in resins. So these cross-linking points are created during a chemical reaction between the monomers, or either between the chains, polymeric chains, and another small molecules. And once these cross-linking points are created, the polymer does not flow anymore. If we apply temperature and pressure, there is no influence on the polymer, since we have a three-dimensional network that has been created with the formation of these cross-linking points. And so, to give the shape of thermosets, we have already to place the initial mixture in the shape, in a mold, for example. Then we provoke the formation of these cross-linking points, and so we end up with the final products. So once these cross-linking points are formed, since we cannot melt and reshape the polymer, so it is much more complicated to recycle thermosets. So some examples of thermosets, as we said, we have epoxy resin, bakelite, and the majority of rubbers. So in thermoplastic category, we can find either amorphous and semi-crystalline polymers. In the case of the thermoset category, we have only amorphous polymers. Now let's introduce the thermal transitions in polymers. So there are two thermal transitions. The first one is a glass transition temperature. That notation is TG. It is the average temperature where amorphous polymeric chains, or the portion of the chain that are in amorphous domains, gain mobility during heating. So below this glass transition temperature, the chains are frozen. They do not have mobility. And through this glass transition temperature, they begin to gain mobility. So in fact, the chains have rotational and translational motions. So we say they present conformational changes. So through this TG, there is a change of polymer behavior. For example, the physical properties of the polymers are modified. The stiffness changes, the heat capacity, and the coefficient of thermal expansion are some examples of physical properties that change. And in fact, through this glass transition temperature, we have a polymer behavior that changes from a more rigid and glass state to rubbery state. The second thermal transition is the melting temperature. That notation is Tm, which is the average temperature where crystals melt and disappear. So below this melting temperature, there is the presence of crystals, so in the case of semi-crystalline polymers. And at this temperature, the crystal melts. We increase, we give more energy to the polymeric chains. They begin to vibrate in the crystals, and the crystals are destroyed. So we have the melting of the crystals. And so below this melting temperature, we have a solid material. And above this temperature, we have a liquid state of matter. And so the glass transition temperature is present either in amorphous and semi-crystalline polymers, whereas the melting temperature is only observed in semi-crystalline polymers. So on this figure are represented the different states of amorphous and semi-crystalline polymers depending on the temperature. So let's start with amorphous polymers. So below the TG, we have the polymer that is in its glassy state. So we said that the chains are frozen. There is no mobility of the chains. Above the TG, we have a polymer that is in its rubbery state. So here the chains are flexible, they can move, and so your polymer is more flexible. And if we continue to increase the temperature, we will see a decrease of the viscosity of this polymer up to observing a viscous liquid. But there is no change of the state of the polymer. Now looking to semi-crystalline polymers. Below the TG of this polymer, we have an ordered state. We have the amorphous portion or the chains in the amorphous region of the semi-crystalline polymer that are frozen, no mobility, and we have the presence of crystals. Above the TG of semi-crystalline polymers, we have the chains in the amorphous domain that gain mobility due to a conformational changes, but we still have crystals. So we said that we have still an ordered state, since in this crystal, the polymer are ordered in a three-dimensional structure. Above the melting temperature, so the crystal disappeared, and so we have a viscous liquid. And if we increase the temperature, the viscosity of this liquid will also decrease. If we continue to rise the temperature either of amorphous or semi-crystalline polymers, the energy given to the system will be so high that it will be able to increase the vibration of the chain and provoke the breaking of this chain. So in fact, we will have degradation of the polymer. It is not represented here, but it is another phenomena that we observe with an increase of the temperature at much higher temperatures. So the value of the glass transition temperature and of the melting temperature depend on the characteristic of the polymers. So let's start with the glass transition temperature, TG. It depends on the flexibility of the chains and the possibility of rotation and conformational changes. So for example, if the size of side group increases, if we have more bulky side group, so the TG will increase because the chains will be much less flexible. So we can illustrate it comparing the value of TG of polypropylene and polystyrene. So you can see that polypropylene and polystyrene have only one group that is different. In the case of polypropylene, we have a methyl group, and in the case of polystyrene, we have a phenyl side group. And you can see that it impacts dramatically the TG. The TG of polypropylene is minus 18 degrees C, whereas the one of polystyrene is 90 degrees C. So having bigger side group make it much more difficult for the chains to have these conformational changes. Then polar side groups and atoms tends to increase the TG. It is because we have, with polar side group and atoms, we have intermolecular interactions between the chains. So if we compare the TG of polypropylene and polyvinyl chloride, PVC, you can see that because of the presence of chloride on PVC, the TG of this polymer is much higher than the one of polypropylene. So due to the interactions through secondary bonds between the chains. Then if we have double bonds or aromatic groups on the backbone, it will difficult the flexibility of the chains. The chains will be much more rigid, and so the TG will increase. The density of cross-linking also increase the TG. And finally, increasing the density of branches will make it more difficult for the chains to move and to have these conformational changes. So the TG increase with the density of branches. Regarding the melting temperature, we can also make a list of some parameters that increase this temperature. So in the same way as the TG was increasing with the size of side group, it is also the case with melting temperature. So in that case, we can compare the melting temperature of polypropylene and polyethylene. So polyethylene has only hydrogen atoms as side groups, and its temperature, melting temperature, is 115 degrees C. Polypropylene has a very similar structure, but instead of having 4 hydrogen side atoms, it has one methyl side group, and this group increases the melting temperature. Then, in the same way, we have polar side groups and atoms that tends to increase the melting temperature because the bond between the intermolecular bond between the polymeric chains involved in the crystal are stronger, and so it is more difficult to destroy this interaction and so to melt the crystals. On the same way, double bonds and aromatic groups on the polymer backbone increase the melting temperature. At low molecular weights, when the molecular weight increases, we also observe an increase of this Tm. And when the side branches increases, on the contrary, we observe a decrease of the melting temperature because as we present in the first lesson, branches make it more difficult for the crystal to be formed. And the crystals that are created are not as perfect as for linear chains. And so because the crystals are less perfect, their melting point is decreased. So the melting temperature is decreased. So something important that I forget to say is that the glass transition temperature and the melting temperature are average value because in fact, if let's take the example of the transition temperature, glass transition temperature. There is not one temperature at which all the segments of the chain begins to gain mobility. In fact, there are some segments of the amorphous region that will be more flexible and will gain mobility at lower temperature, and other parts at a slightly higher temperature. So the glass transition temperature represents an average temperature for this transition. In the same way, regarding the melting temperature, the value that we will consider will be an average value because since we have melting of the crystals at the melting temperature, we should consider that in a polymeric sample, not all the crystals will have the same characteristics. And so some lamella will be a little bit more thin and other a little bit more thick. And so the first one will have a melting temperature a little bit lower and the other one a little bit higher. And so there is a range of melting temperatures. And when we are going to talk about the melting temperature, we are talking about the average temperature where at which the crystals melt. So at the glass transition temperature and at the melting temperature, we have a change of physical properties of the polymer. And before talking of polymer processing, we can have a look to this figure that represents the evolution of the specific volume of a polymer with the temperature. So first of all, let's have a look to a 100% amorphous polymer. So in that case, we will only have a glass transition temperature and no melting temperature because there is no crystals. You can see a continuous increase of the specific volume with the temperature at the TG, but the increase of the specific volume with the increase of the temperature is much higher above the glass transition temperature because due to the higher vibration of the chains that gain mobility above the TG, the specific volume of the material increases in a higher extent. Then let's have a look to a 100 perfect crystal, which is 100% crystalline. In that case, we have only a melting temperature and no glass transition temperature because there is no amorphous portion. There is a dramatic increase of the specific volume of this material at the melting temperature. Why? Because in that case, below the melting temperature, we have all the polymeric chains that are perfectly ordered in crystals, which are dense regions. So the chains are packed into the crystals and the crystals are dense portion. And so at the melting temperature, the crystals are melted, and so we end up with like a 100% amorphous polymer. And so the space between the chains in the amorphous state is higher than in crystals. That's why we observe a sudden increase of the specific volume. But a 100 crystalline polymer does not exist. So either we have a 100% amorphous or a semi-crystalline polymer. So in the case of a semi-crystalline polymer, we will have a glass transition temperature corresponding to the change of mobility of the amorphous portion of the semi-crystalline polymer, and a melting temperature corresponding to the melting of the crystalline portion of the semi-crystalline polymer. Okay, and so we can observe a continuous increase of the specific volume with the temperature at the TG, like it was the case in the 100% amorphous polymer. And we observe a sudden increase of the specific volume at the melting temperature due to the melting of the crystal, as we explained with the case of the perfect crystal. And so, to summarize, above the melting temperature, all of this material will be 100% amorphous, so all of them will have the same specific volume. So this specific volume is explained by the volume occupied by the atoms of the polymer, and also by a volume, a free volume between the chains. So that's why for the same temperature, below the melting temperature, for the same temperature, the specific volume of the 100% amorphous is much higher, because there is a large free space between all the chains, and this specific volume will decrease with the increase of the amount of crystals in the semi-crystalline polymer, due to the fact that the chains are more packed in this region, and so the free volume in the semi-crystalline polymer will decrease. And so this graph is very important when we deal with polymer processing, because depending on how we melt, at which temperature do we process our polymer, and at which temperature it will be cooled, we will have a change of the expansion of the polymer, of the volume of the polymer, and so a change of the dimension of the matter. And so we should take it into account when we deal with material processing and with polymer processing, in order to know how the material will, for example, shrink during cooling, because it will give us information of the final dimension of our products. So the thermal transitions are very important because they define the range of temperature at which we can use these polymers, and also the properties of the polymers depending on the temperature. So first, for the thermoplastics, if we have an amorphous thermoplastic, we will only have a glass transition temperature. And if we use this polymer above the TG, we will have a viscous material, viscous liquid, whereas if we use it below the TG, we will have a hard and more brittle polymer. In the case of a semi-crystalline thermoplastic, so in the same way, below its TG, we will have a hard and brittle polymer, rigid polymer, and between its TG and its TM, we will have a soft and more flexible polymer. Of course, if we use this polymer above its melting temperature, we will have a melted polymer. And so in the case of semi-crystalline polymer, for their processing, we will process it above its melting temperature. In the case of thermosetting polymers, they are amorphous, so they have only a TG. In the case of rubber, we have materials that have a very low TG, And so at the temperature of use, since we want a flexible material, we will use them above their TG. On the case of thermosetting or resins, we have a material with a high density of cross-linking, which is rigid, and so the TG of this material is very high. So the temperature of use of resins is below their TG. So finally, we can have a look to this table that summarize typical TG and TM values for a list of polymers. You can see that some of them do not have any melting temperature because they are amorphous. For example, polybutadiene is a cross-linked elastomer. Its TG is relatively low, minus 100 degrees C. So we can use it above this temperature up to high temperature, and we have a flexible polymer elastomer. A very common polymer, semi-crystalline polymer, is polypropylene. So you can see that we can use polypropylene between minus 16 degrees C up to 170 degrees C. Below this temperature of minus 16 degrees C, it is rigid and brittle. So we use it above this temperature and below its melting temperature. And polytetrafluoroethylene is also a semi-crystalline polymer, but you can see that its glass transition temperature and melting temperature are much higher than the other polymers, because in that case, we have the presence of fluorine group as side groups that can interact with very strongly with other chains. And so this explains this high temperature. So in order to melt this polytetrafluoroethylene polymer, we will have to reach a temperature above 330 degrees C. So, now, after having presented the thermal transitions of polymer, we are going to present polymer processing. So polymer processing is a step through which we transform a raw material into specific products. And so if you want to fabricate a specific product, what are the information you should take into account to choose the most adequate processing technique? So in fact, we will have to take into account a series of criteria. So first of all, we have to know if the material to be processed is a thermoplastic or a thermoset, because we saw that the structure is different and the thermal properties are different. Then we should have a look to the temperature at which the material is softened or at which it's flow in the case of thermoplastics. So we should have a look to a TG if it's an amorphous polymer, or we should have a look to the melting temperature. Then we should take into account the chemical stability, because polymers can degrade, and so we should avoid it during processing. So taking into account the resistance to oxidation or the mechanical degradation during which we observe a decrease of the molecular weight of the chains, they are broke during the process. This should be taken into account. We should avoid it, and we should select a processing technique that will avoid conditions that would provoke the material degradation. And finally, the geometry and size of the final product is an important criteria, because some technique will allow more complex geometry, and other one will permit to produce much bigger product. And so we should take it into account during the selection of the best processing technique. So for polymer processing, generally, we will use temperature and pressure. So we will start with a raw polymer, which is either a powder or pellets. So pellets is this kind of short pieces of polymer. And we will plastify this polymer through the plasticization step. In this stage, either we will work above the melting temperature of semi-crystalline polymers or above the TG of amorphous polymer. And during this step, we will be able to mix this polymer with other additives, like dyes, like other polymers, other particles, and so on. And after this plasticization step, where we apply generally mechanical work on the polymer, where we apply temperature, so the polymer will flow, and it will go to a shaping step. So we have different techniques to give the shape to a molten polymer, like extrusion, molding, injection molding, blow molding, and other like casting, calendering, and so on. So during this shaping step, the shape will be given to the final product. And in order to maintain this shape, we should have a stabilization step of the shape. So depending on the class of polymer we are working with, this will be possible using different strategies. So in the case of thermoplastics, solidification will be obtained by cooling the molded product, so below the melting temperature in the case of semi-crystalline polymer, or below the TG of amorphous polymer. Whereas in the case of thermosets, the shape will be stabilized through the chemical reaction that will create cross-linking. And so generally cross-linking is produced by an increase of temperature. And so we will select conditions that provoke this cross-linking reaction in thermosets. And so after the stabilization of the shape, we can remove the product from, or we can obtain the final product. We can remove it from the mold. So there are different techniques for polymer processing, like continuous processing techniques. The most common is extrusions to fabricate films, fibers, sheets, blow films. Then we have molding techniques such as injection molding, compression molding, transfer molding, rotational molding, and so on. And also a combination of extrusion and molding, which is blow molding. This list is not exhaustive, and so other techniques can be found in the literature. So extrusion is the most used type of processing technique for polymers. In Brazil, almost 63% of the products are produced by extrusion, and it is a continuous process used for elastomers and thermoplastics. So an extruder is composed of different parts. There is a feed hopper in which you place the polymeric pellets and the additives, the fillers, and so on. You have a screw that is rotating thanks to an electric motor. You have the barrel that is heated, And at the end of this barrel, you have a die, which is a small hole which gives the shape to the product. So let's see a video to understand how does it works. So let's watch a video that explains how the extrusion process works. So here is a representation of the extruder. There is the hopper in which we place the polymeric pellets and the fillers, the additives, and so on. They will fall on the screw, and we have a screw that rotates thanks to a motor, and this screw conveys the plastic forward in the heated barrel. So in red are represented the heater, and so we control the temperature of the polymer, and so the polymer will melt and it will be compressed between the screw and the barrel. So this pressure will facilitate the mixture of everything, of the polymer and fillers and additives and so on. And at the end of the screw, the polymer is totally melted and it is compressed to go through the die. And so the shape of the die gives the shape of the product, polymeric product, and the size of this product. And after that, either we work with a thermoplastic, and so we need to decrease the temperature of this extruded part. So, for example, in that case, it is represented a cooling bath. Either we have a thermoset, and in that case, it is not a cooling bath, but an oven in order to increase the temperature of the extruded parts. To provoke cross-linking to fix the shape of the thermoset part. And in that case, we have a next step, which is which aim at cutting the polymer, the extruded polymer. So films and tubes and such profile are produced with extrusion. So here we found again the 3 steps necessary to produce this product. Plasticization occurs in the screw. The shape is given by the die, and stabilization of the shape occurs on the product once it exits the die. So there are variations of the extrusion process, and one of them is a blown film process, which is used to create garbage plastic bags or used the film used in packaging. So in the blown film process, a bubble is created in order to obtain a plastic film. So in this video, I presented different extruders. So more simple process, only use one extruder in order to create the plastic bubble. In that case, various extruders are used in order to obtain a bubble composed of different layers, so different polymer composition. So in each extruder is processed different composition. So each extruder will produce a cylindrical tube, and we have pressurized air that is blown inside the tube, and this enables to increase the diameter of this tube and to create a bubble. This expansion of the diameter is possible because at this step, the polymer is still in its molten state, so its viscosity is high, but it's still possible to modify this diameter. And so we obtain a tall and thin and continuous bubble that is produced vertically. And as you can see, there are rolls on the top of the bubble that control, that also enable to control the alignment of the chains and the properties of the polymer. And after that, in this step, so all along, the polymer is cooled, and then the film is stored on rolls for then being used. So during this process, we have the air that enable to increase the diameter of this bubble. During this process, we have the modification of the orientation of the chains. So we have chains that are going to be more aligned on the circumference along the circumference of this bubble. And at the same time, since we have the two rolls on the top of this bubble that push this bubble vertically, we also have a pressure that aligns the macromolecule on a vertical position. So some of the chains are aligned perpendicularly and some of them horizontally. So on this figure, we have a better representation of the coupling of the extruder and of the system that enable to blow air through this die. So along this process, we have orientation of the polymeric chains. We have first the pressure of the air that increase the diameter of the bubble, and when this occurs, we have a polymeric chain that get orientated along the circumference of this bubble. At the same time, we have two rolls at the upper extremity of the bubble that push this film to be stored on the rolls, and while pushing these films, it creates a tension of the bubble vertically, and this enables polymeric chains to align on the vertical direction. So this process enables a B orientation of the chains. So some are aligned along the circumference of the bubble and others are aligned vertically. And this impacts the properties of this film, which are very important for example, for plastic bag, when we want to ensure mechanical resistance in the two directions of the film. Another variation of extrusion is the combination of extrusion and molding. So we call it the blow molding process. So in that case, we have an extruder that will form a tube, and we will couple it with mold. So for example, in that case that is represented, it is a mold in order to create a bottle, so to give the shape to the bottle. The extruder will form a tube, and this part of the tube that will serve to produce the product is called parison. It is like a pre-shaped part. Once it is produced, the two parts of the mold will close, and it will enable to close the bottom part of this parison. And then on the upper part, there will be air that will be blown into this parison, and the pressure of the air will permit to expand this parison that will be pushed on the walls of the mold. And after a certain time, then the mold is cooled, in order to fix the shape of the product. And once the product is shaped, so the product is released by the mold open. So for example, all the plastic bottles are created or can be created thanks to this process. And also hollow parts, such as the ones that are represented here, are produced thanks to blow molding process. Another common process is injection. It is a batch process used for thermosets and thermoplastics. So in injection molding, the melted polymer is injected into a mold. So here is a representation of a mold. It is composed of two parts that, once closed, form a cavity. So let's see how does it work. So as you can see, the injector has a part that is quite similar to an extruder. So we have a screw, a barrel, so the polymer and additives and so on is fitted in the hopper. It falls on the screw rotates, the polymer is melted and pressurized, and the melted polymer is stored on the front of the screw. So as it is represented. And once the necessary volume of melted polymer is stored on the front of the screw applies a pressure on this melted polymer in order to send this melted polymer in the mold. So it will fulfill the mold, and then the mold will be cooled in order to fix the shape of the thermoplastic in that case. And once it is rigid enough, the product is ejected from the mold is open and the product is ejected. So of course, if we have a thermoset, there is no temperature here in the barrel. The viscous matter is sent into the mold. The mold is heated in order to provoke the cross-linking of the thermoset. And once the shape is given to the polymer, it is ejected from the mold. And as you can see, this process permits a high productivity. So in this process, we have the plasticization that occur in the barrel, thanks to the screw and thanks to the temperature applied on the barrel. The shaping is due to the mold that gives the shape to the product, and the stabilization of the shape is performed during the mold cooling or during the cross-linking reactions that occur in the mold. And so this process is used to create big products or products with a very complex shape, like the panel of your car, for example, or this plastic chair, or also these Melissa shoes. So injection molding is a technique using a mold. Another and more simple technique using a mold is compression molding. So it is also a batch process for thermoplastics and thermosets. So on the right part of the screen, you can see a figure representing how this process works. So you have two parts of the mold, a lower fixed part, and the upper part can move. So you will place a charge, which is the amount of polymer necessary to create the product. You place it on the lower part of the mold, and then you will press the upper part of the mold like shown on this picture. So, and the pressure applied on the polymer will force it to flow and to fulfill the cavity of the mold. And of course, we will use temperature in case of amorphous and semi-crystalline polymer to facilitate the flow, to permit the melting of the polymer and facilitating the flow of the polymer to fulfill the cavity. So once again, we apply pressure and temperature. In that case, with thermoplastics, we will have to wait for a certain time after the polymer fulfills the cavity in order to cool the mold and to fix the shape of the product. On the left part of the slide, you can see a reaction in order to illustrate what would happen in the case of bakelite, of a thermoset resin. So bakelite is used and will be used in the second practical class of materials and their properties in order to perform the analysis of metal microstructure. And so the parts of the metal will be fixed in a bakelite structure. And you will see that in this process, we will start with the raw material, which is two monomers, composed of two monomers, phenol and formaldehyde. We had a catalyzer, and we place it in the lower part of the mold. After that, we apply heat and pressure in order to permit to this resin to fulfill the mold and to get the adequate shape. And during the reaction, we have high molecular weight molecules that are produced and cross-linking between these molecules. And this results in the formation and the obtention of bakelite. Then the molded product is cooled and we get our final bakelite products. So now let's talk a little bit about additives. So many of the polymer properties are intrinsic. They depend on the molecular structure of the polymer. But in some cases, it is necessary to tune the properties of the polymer, to modify it. And in that case, we use additives. So there are small molecules or particles that are added to the polymer in order to add a specific property. So, for example, colorants are a very known additive and very easy to understand how it can impact the properties of the polymer. So in that case, we want to change the color and change the optical properties of the polymer. So either they are dyed or pigments and they are mixed with the polymer in its molten state in order to give the color to the final product. Then we have flame retardants. So polymeric materials have a problem, they can burn, and during the burning of the polymer, it can either so the majority of polymer properties are intrinsic and depend on the molecular structure and the chemistry of the polymers, but it can be necessary to modify these properties, for example, to modify the mechanical, chemical, physical, optical properties of the polymer. And in that case, we use additives. So now let's talk a little bit about additives. We have different classes of additives. So here we have some examples. For example, colorants are used in order to change the optical properties of the polymer, to add, for example, a specific color to a product. So these organic or inorganic dye are mixed with a molten polymer. Either it can maintain their transparency or can transform the polymer into an opaque polymer. Then we have the flame retardants. Polymer have the the problem to be flammable. And in some application like textile or in children's toys, it can be very important to limit the flammability of the polymeric product. So in that case, the flame retardant additives are added to the polymer to increase the flammability resistance. And these retardants function in different ways. So either it interferes with the combustion process, so limiting, for example, the creation of gases or creating gases that will limit the combustion, or by initiating a chemical reaction that will cause the cooling of the polymeric products. So different additives of flame retardants may have different actuation on the flammability and on the burning process. Then we have fillers. So for example, carbon black is highly used, but also calcium carbonate. Fillers have two main objectives, either to increase the mechanical resistance of the polymer, either to decrease the price of the polymer, because some of the fillers are much more cheap than polymer. And so if you replace part of the volume of the polymer with fillers, so you can decrease the price of your product. So we have different kind of fillers, and we should take into account the affinity of the polymeric chains for the different kind of fillers, for the chemistry, for the structure. It will be very important to evaluate these parameters in order to select an appropriate filler. On the left part of this slide, you can also see the example of antioxidants and stabilizers, because polymers are susceptible to degrade either due to the actuation of UV light or thermal oxidation, and it will cause the decrease of the molecular weight of the polymer. The chains will be broken due to the action of oxidation, of light, and so on. And so in order to avoid this process that can, as you can see, in that case, it's impacted a lot the aspect of these fibers and also the color of this product. So we can add some antioxidant and stabilizer molecule to avoid the impact of this agent, like light and oxygen, on the macromolecules. Another kind of additives are the blowing agents. So they are willingly added to the polymer in order to create a foam. So in some application, it can be necessary to not have a bulk and dense polymer, but to create porosity in order, for example, to absorb acoustic vibration, or either to create lighter products. So in that case, we add blowing agent that during the process and generally under the action of heat will degrade and will release a gas. And this gas will be responsible for the creation of these pores in the polymer. And so during this process, when the polymer, at the end of the process, when the polymer is cooled down, so there is the rigidity of this polymer will maintain the formation of the pores created by this gas. And then we have plasticizers. So let's talk a little bit more about plasticizers. So they are very important additives in polymers because they permit to increase flexibility and ductility, or they can help makes the processing of polymer easier. So they reduce the hardness and the stiffness. In fact, plasticizers are small molecules that will find a place between the macromolecular chains and will create free volume between these molecular chains. And by creating these spaces between the chains, it will facilitate the movement of the chains. And so, as a consequence, it will reduce the glass transition temperature of the polymer. So, for example, these plasticizers are highly used to convert PVC, polyvinyl chloride, from rigid to flexible polymer. So it's interesting because plasticizers are additives that directly impact the thermal transition of the polymer. So we can modulate this thermal transition. And some plasticizers that are highly criticized are phthalates. So you may have heard about these plasticizers because, for example, the European Union banned the use of these plasticizers in the baby bottle because it was perceived that they are toxic and they were impacted the health of children. Because these small molecules, since they are not attached to the molecular chains and they have a low molecular weight, they can migrate between the molecular chains and they can reach the superficie of your polymer products. And along the time, this is a process that is relatively slow, but along the time this migration occurs, and once it's reached the superficie, the surface of your polymer product, it can be transferred to another media. And for example, in that case, it was transferred to the mouth of the babies. And so that way it is very important to study the toxicity of these plasticizers and also to observe if they migrate along the time in your polymer or not. Some of them don't migrate, and so it is another field of study in polymer science. So finally, let's talk a little bit about polymer recycling, because when we are thinking about pollution, generally we think about plastics and the polymers are pointed out. But in this class, we introduce the fact that a large part of polymers can be recycled. And so what is the real problem? Is it plastics or a good recycling practices? So it is very common to see these kind of pictures that point at plastics in their single-use product or application. So of course we should think that the pollution would be reduced by reducing the use of plastic, reuse the product formed by plastics, but also we should think about recycling and developing new recycling possibilities and recycling ways. So polymer recycling starts with the action of the consumer. So after using the polymeric product, the consumer should separate this plastic into separated garbage in order to enable the process of picking up these plastics, transfer it to a specific recycling unit. And after that, there is different steps. So first of all, there is an inspection of the plastic trashes to see if there are some contaminants and to identify if the plastics that are present in this garbage can all be recycled or not, because we saw that thermosettings polymer cannot be recycled in the same way than thermoplastics. And so after that, there is a washing of this polymeric product and shopping, which is the process to create small flakes, which are a small particle of polymer. And after that, there is a separation of plastics of different nature, of different chemical composition, by their density, because each polymer is composed of different chemical groups and so on, and so they have different density. So to make this separation, there is a succession of flotation tank that contain different kind of solvent. So in each tank will be a specific solvent with a specific density. And so the flakes will be placed in a solvent, and after a time, there will be some flakes remaining on the surface of the solvent, which means these polymers have a lower density than the density of the solvent, whereas the other one that sink to the bottom part of the tank have a higher density than the solvent. So we make this first separation. And each time the part that flow and the part that sink is placed in another solvent, and so on and so on, in order to make a refined separation of all the different plastics. So after that, the different flakes composed of different plastics are dried and melted. And once they are melted, they are filtered, because sometimes there are some particles, additives like fillers that are still present in these polymers. And so it's enabled to remove such kind of small particles. And after that, the polymer is pelletized, which is the step that enables to produce new pellets that can be used in another process. Okay, so this is what is done for thermoplastics. For thermosets, other way of recycling are implemented. For example, rubber are cutted in small pieces, and it can be integrated to other products for civil engineering, for example, so material for building, in order to increase the impact resistance, or in order to increase the absorption of vibration of these kind of products. And so by working on polymer recycling, we can, instead of having plastic polluting nature, transforming them into new products. And so, for example, these nice coffee pots are made of recycled polymer, so it does not seem to be recycled. It is a nice aspect. And also it is used in textile. For example, these shoes are created with recycled polyethylene terephthalate, which is a common polymer used in plastic bottles. In other way, it is also possible to develop new polymers that can, for example, be dissolved in a specific solvent a long time. So after its use, we could place it in the solvent, and after some weeks, we could obtain this kind of solution and separate the solvent and the polymeric chains and process it reprocess it in order to form another product. So you can see that there are different possibilities for polymer recycling, and we should work on developing more recycling routes in order to avoid pollution by plastics. So thank you very much. You will find some exercises to prepare on the TGE. And if you have any doubts, you can send it on TGE, or you can wait for the next question session that will be on Wednesday, the 6th of May at 5 o'clock. Thank you very much.